So in this case, what's the final value of the capacitor voltage going to be in this case?
It'd be your VS.
The same as the voltage source?
Yeah, same as the voltage source, VS. So, but the thing that happens here is, in a circuit like this, how much current is flowing once I reach steady state?
None.
None. Basically, there's really nothing happening in the circuit. I'm basically taking energy from this voltage source, transferring it to here, and then that's it. The circuit's done. Nothing happens. And there go the lights again. I guess I'm going to be stuck like this. So the thing that's weird, about, a first order circuit, or what's different between a first order circuit and a second order circuit, first order circuit, things stop happening. But in a second order circuit, that's not necessarily the case, okay? I can kind of get what I would think of as quote unquote strange interactions. And the reason is because the energy storage elements can transfer energy back and forth between themselves, potentially losing some energy in the process. So what happened in the first order circuit is if I look at, this guy on the left here that's discharging, if I get that capacitor charged up to 5 volts, explain to me physically what's happening if I charge this capacitor to 5 volts and I put this switch in position 2 like it is right here, what is physically happening? Explain to me the physics of that situation.
Would it just dissipate throughout the entire circuit?
It's dissipating in the resistor, basically. It's the energy that I store in the capacitor is lost as heat in that resistor, right? The resistor will get hot and the energy will be gone, okay? So physically, I'm losing energy. So resistors always represent the loss or use of energy, okay? Whereas the capacitor is the storage of energy, or the inductor is the storage of energy. So, I'll start with, to explain second order systems, right? I want to kind of think about second order systems in kind of a basic physics way, because really second order systems they occur a lot. And we're going to look at example here before I kind of start getting into how to utilize or how to approach the solution, right? But the pendulum is probably the first place that I will begin, because it's probably the first second order system you ever really experienced, right? So simplest thing would be if let's say you were, still a little kid and you had your butt sitting on a swing right here, right? This is basically, the pendulum is basically a kid sitting in a swing. And so I've got a little simulation here that kind of walks through, how does this guy behave? So if you guys know enough from physics, right? So when I have the ball sitting here and I say I'm basically sitting this guy at an angle of 20 degrees, okay? So let's say this angle theta is 20 degrees. And let's say where the black line is, let's say that's 0 degrees. And let's say if I go over this way on this side of the black line, the left side, let's say that's negative angles, okay? When I have this situation where the ball is sitting here and I let it go, it's going to swing this way, and the ball is going to drop its height a little bit, right? So the way you thought about this in physics is what? When the ball is sitting here and it's not moving, what kind of energy does the ball have?
Potential energy.
Energy, right? And when I drop it, basically,
I think it is a kinetic energy.
Yeah, when I drop it, I lose the potential energy and I get the kinetic energy, right? So essentially what happens is I start out initially with a whole bunch of potential energy. By the time I get to the bottom, basically at a height of 0, we say I have all kinetic energy. And then by the time I swing back to the other side, what happens then?
You should be at the same angle you were initially at.
I should be at the same
Your
angle.
potential energy increases.
Yeah. What was that?
When the pendulum swings again all the way back to the other side at the same angle, you already have you have more potential energy.
Well, I should have
right?
the same amount that I started with, right? So ideally, if I started with some potential energy, I'd be at this angle 20 degrees, and I would get all kinetic energy at the bottom, and then I would ideally rotate back to 20 degrees on the other side. And I would just go back and forth like that, okay? Basically what's happening is I put potential energy in the system by grabbing the ball, and then I convert that potential energy to kinetic. And then as he slows down going up, all that energy gets converted back to potential, and it just sloshes back and forth. Now, in that particular case, right, that's an ideal case, because if that's the case, if I start out at 20 degrees get to 0, then get to -20, then back to 0, then back to 20, then back to 0, then back to -20. What's that assume about this system?
There's no gravity.
Not that there's no gravity.
There's no
There's
resistance.
no loss in the system.
There's no loss in the system. Yeah, right. So where would loss come into play here? What would be the most common place for loss?
Air resistance.
In the air resistance and
Some air resistance. Yeah, some air resistance, and probably also if this joint up here was a little bit, frictiony, let's say. So some form of friction. So that friction is a lot like what a resistor does in a circuit. Okay, we're gonna talk that through here a little bit as we go. But I like this analogy because it's a really simple one. So if I think about what that angle theta is going to look like, it's going to start at 20 degrees, go to 0, then get to -20, then back to 0, then up to 20. If I looked at what the angle theta looked like over time, what would it look like? Like if I drew as a function of time, theta of t, right? What would theta of t look like?
An oscillating wave.
Yeah, it would start out at 20 degrees and it would continue like that, okay? So I made, so basically what I did was I took this guy and I simulated it using a tool called Simulink, which is part of MATLAB, right? It's not a tool that you guys are being asked to use here, but it's a tool that I'll use from time to time to make some demonstrations on things, how circuits and things work. So if I go to this, all right, so let me make this full screen here. All right, so what I did was essentially to set up this little demonstration system here. So here's my pendulum. And if I run this pendulum essentially with no losses, the theta looks something like what I've shown right here. Now, if I take this guy, and I need the lights because I need to see my notes. All right, what I do is I run this a little bit, and eventually what I do, and you can watch the whole video, it's linked here if you want to. All right. So I think what I do is I change about this thing. I change the friction here. All right, so let me pause it for a second. What I do is I change the friction in this, right? When I change the friction, if I go forward a little tiny bit here, the friction, hopefully you guys can see that on my screen there, it says damping coefficient, right? So I changed something about this thing called the damping coefficient. And when I change that, and then I run the model, all right, essentially what I get, I guess it's not playing, there we go. Yeah, so let me let it run. Okay. All right, so now if you watch the ball, right, it spins back and forth, but it slowly comes to a stop because so some of the energy that started out as potential energy gets lost as I go. So the key thing is I still see a sine wave, right? But what do you notice about the amplitude of that sine wave?
It's
decreasing
slowly
over
coming
time.
to 0.
Yeah,
It's
it's
just
slowly,
kind of damping.
yeah, it's slowly coming to 0. So in other words, what this guy is he's a damped system, all right? What I call this an underdamped system. Now, you may have seen a little bit of this in physics. You may have seen a little bit of this in differential equations. You may see a little bit of this as well in 2254. This kind of dynamic behavior of a second order system is really important because a lot of the engineered systems that we have in the real world have this kind of behavior. Like, so for instance, this pendulum. All right, I'll show you an example in a minute where I'm looking at what I call a photovoltaic converter. So a device that basically converts energy from a PV panel, solar panel, to the grid, right? It has some of these behaviors as well. Lots of systems have this behavior, and so it's important for us to do this. If I'm in robotics, right? This actually models kind of the behavior of a robot arm, and I might be trying to control that with an Arduino or a microcontroller. Well, typically I might see behaviors like this in the motion of that robot arm, right? And maybe I don't want a robot arm to have its angle look like this, okay? Like over time, I don't want this kind of damp behavior. So let me ask you this. Let's say I don't like this oscillation. I want this oscillation to go away. What can I do to this system to make this oscillation here go away? What can be done physically such that So let me just to go back for a second. Here I have oscillation, and the oscillation is not decaying. How much loss do I have in the system when I don't have the decay?
Zero.
Zero, right? So when I introduced a little bit of loss, I got to a situation where it decays over time. What happens if I jack that loss up? In other words, I make the friction get really high. What's this response going to look like when the friction gets really high?
Even lower.
Basically just go straight to zero.
Well, it may not go straight to zero, but at the very least, what I'll see is as I change that, so here, you know, I increased it a little more. And all right, now I see it still oscillated a little bit. Like I'd call what I see on the screen a little bit of an oscillation where it goes down and it overshot a little bit. So if I roll back the video a little bit, I see a little bit of the overshooting. All right, so here I'll run the simulation. I'm probably talking on the video, and that's why it's running. I'll just skip ahead, right? All right, so what I do is when I increase that loss in the system, what happens is it still has this oscillation. So it starts at 20 degrees, goes a little bit negative, but more quickly settles to zero. The oscillation goes away. And if I really increase it, right, so I increase it one more time, now I see this. Now, when you look at that, this now looks pretty similar to what? Well, to me, this looks pretty similar to the voltage in a first order system. Like if I looked at, you know, the capacitor there, right? So if I looked at my capacitor in my first order system, that looks pretty similar to what the voltage does on that capacitor. So it's almost like I've taken that second order system and I've almost kind of made it a first order system, all right? So in this case, I've made the loss really big. So the thing about a second order system is, and the reason I like to say it this way is I can get this weird interaction between the energy storage elements. So in this case with the pendulum, what I'm saying is with my pendulum, I start with basically all potential energy, convert it to kinetic, get it back to potential on the other side. And what's happening, this oscillation is basically happening because the energy storage elements with no losses are just sloshing energy back and forth between them, okay? Now, I point that out because to me, that physics is kind of important. This type of thing is used to create an oscillator. So for instance, your phone has a circuit that basically has almost no losses, basically zero losses, so that it can create a sine wave that basically is the signal that your phone sends out to the cell phone tower, okay? And there's a circuit inside your cell phone that, all right? You know, so this idea is particularly important. What this also says that is if I have no losses in this system, then essentially the currents and voltages can go on forever, right? Basically energy just keeps getting sloshed back and forth. All right, now I start out with the pendulum model, right? But it's the same thing basically if I have a circuit, all right? So in this particular case, what I have is now basically what I'm going to call an LRC circuit. All right. Now this is a picture from this tool I call Simulink. So what I have is a resistor, an inductor, and a capacitor. And this guy right here is a current sensor. And this guy right here is a voltage sensor. So I'm measuring the voltage across the capacitor and I'm measuring the current through the inductor. And I've given you the parameters that I have here. So I basically am trying to do something pretty similar to what I did in my pendulum. In my pendulum, I started out with all potential energy. Here, I charge up my capacitor to 10 volts. That's like starting with all potential energy. And then I slosh it over to, so I start with all energy here. What's going to happen eventually to the voltage on that capacitor? It's going to drop to zero. And where's it going to go? Where's that energy going to go if my losses are basically zero?
To the inductor. To
the inductor, right? So I'm basically going to go from having a bunch of voltage here to basically having a bunch of current, all right? So and what I do here in the video, if you watch this, is I go from basically taking the resistor from 0 up to 10 ohms. So I'm increasing the losses from nothing to something pretty big. And so if I just go real quick, I won't go through this in excruciating detail here. but I'll take a quick pass at it. All right. So this is basically, in this case, a situation where I have no loss in the system, right? And so the top here, the yellow, is the voltage on the capacitor, and the purple is the inductor current. So what should be true about when the voltage on the capacitor is at a maximum? What should be true about the current when the voltage on the capacitor is at a maximum?
Should be zero.
Zero.
Yeah, the current should be 0. And if I look at that, I think I zoom in on it here. Let me zoom. At some point I zoom in on it. Yeah, once I zoom in on it, you see that more carefully, right? So when this guy reaches his peak, he's basically at a 0, all right? And I'm getting this sloshing back and forth between the energy. Now what I do here is eventually I increase that resistance from 0 to something that's still pretty small, but you know, a little bit appreciable, and then run the simulation. And I get something like this. So again, with this, in this case, I think this is with 0.01 ohms of resistance. So I went from 0 to 0.01. I see the voltage drops over time, but still oscillates. And the current drops over time, but still oscillates. All right, this guy, I give the name to what? So let's see if you guys know. What do you, does anybody know what this is called, this type of response?
Is it a dampened response?
It's dampened, yeah. We give a specific name to it. I called it, and we're going to talk about this in a lot more detail here in a minute, but I call this an underdamped response, all right? The initial piece right here, we don't really talk about this very much because in nature, it's really hard to get this response where it doesn't decay. It does happen. Like I said, your cell phone does this, but there's some magic happening with transistors and things to make this happen. Nature doesn't want this to occur on its own, right? We have to do some man-made things to overcome nature to make that happen. This response, this ideal response, I call undamped or not damped, okay? And then I get to this guy here, right, which I call underdamped, okay? And if I continue to increase the resistance in the circuit even further, right? So I think, let me try, all right, here's, do it here, okay. All right, this is with a slightly higher resistance. I still see a little bit of oscillation. What I call this is a little bit of overshooting, where basically what's happening is if I look at the voltage, it goes below 0, then it goes above 0. So it's that below and above 0. Sometimes we call that overshooting, okay? This is also what I would call an underdamped response. Eventually.
Excuse me, Dr. Cox.
Yeah.
I have a question. So we're talking about LRC circuits. We said earlier that the resistors represent the use or the loss of energy.
Yes.
Capacitors represent the storage of energy. What would you say that the inductors represent?
Well, inductor is also a storage of energy, right? So in a capacitor, you're just storing energy in an electric field in the capacitor. And in an inductor, you're storing energy in the magnetic field. Yeah, right.
Okay.
Yeah, good question. All right, so if I look at, you know, eventually as I increase that resistance, if I look at this guy right here, I see it just drops below 0 and just levels off. This type of behavior where I've kind of lost all of that kind of oscillation behavior, all of that kind of sinusoidal behavior, I call this overdamped, okay? So essentially, when we get into second order systems, our responses, they're always exponential, but they can be complex exponential, all right? So Yawu will be talking to you about what that means in 2254. But essentially what it means is I can potentially have a decaying sinusoid, or I can get something that looks like a first order response, like what I have right here, okay? All right, so we're gonna talk about all this in more detail, but I wanted I like to start out with a little bit of a physics, you know, understanding of the significance of that stuff. All right, and I try to say, you know, this does happen in reality in all kinds of places, all right? One example, you know, that I like to think about is if I have, this is what I call a photovoltaic inverter, all right? So an inverter is a circuit that basically takes a DC input, which would be, you know, I'd put a DC. So again, let me ask this. What does DC mean? When I say the word DC, it means direct current.
Direct.
Right?
Direct current.
But what does direct current mean? If you had to tell me what a DC source is, what would a DC source be?
It's a constant.
Constant.
It's constant.
From the source.
Yeah, it's a constant source, right? So basically, if I had a solar panel over here, that solar panel would be a constant current source, is what it would actually be. This thing over here, you know, with these weird blue devices that I have right here, you're going to learn more about those. What they are switches. They turn on and turn off. And we give those switches a name, which is transistors, all right? But all a transistor is a light switch, basically. It's a semiconductor version of a light switch that turns on and off particularly fast. If I take a constant voltage and I put it through this switch network, then what I'll get over here on this side of the system is an AC voltage, okay? All right, so if I look carefully, you know, in some of these cases, what I'll see, if I look at the voltage across one of these devices, what I'll see is that the voltage will look something like this, which is an underdamped second order type of response, okay? These happen all the time. These happen in digital circuits. This guy here is basically a form of a digital circuit, all right? So behaviors like this happen and they potentially could be bad. In this case, this is an underdamped response. And what it means is potentially maybe my voltages get to be too high and they cause problems within my circuit. Okay, so we, you know, understanding the behaviors of these second order circuits is particularly important. Now, what we're going to do after we talk about this is we're eventually going to go to just considering other sources than constant sources, right? We're going to get to considering true AC sources, meaning sources that vary as a function of time. But we need to first kind of understand these sort of dynamic behaviors that happen in transient first. But there's all kinds of examples I could think about, both in digital circuits, in electromechanical systems where this kind of behavior sort of occurs. All right, so it's really important for us to understand the basic ideas of second order systems. Okay, now Zybooks does something that I'm not a big fan of. They have this whole big chapter 6 on second order circuits, and it has a couple of sections on what they call series LRC circuits and a couple of sections on parallel RLC circuits. And eventually it gets to this sort of section 6.10, which is the general approach. I'm going to start right there in the general approach. And I'm going to take it from the general approach. There's way too many equations in Zybooks, in my opinion. I'm going to distill it down to the equations that I think are most important. And that was actually why I didn't send you guys anything to look at in advance. I have some stuff for you guys to look at in advance on Canvas for Wednesday, but I wanted to kind of walk you through it myself first, because to me, it's a little bit more important to have that physical intuition about it. Now, Zybooks basically has what they list as is 5 steps to these problems. So you remember, I gave you guys 5 steps to solving first order circuits. I have a similar process for trying to walk through second order circuits, okay? And today, I'm basically going to start on the first couple of these, and then we're going to talk about the other ones on Wednesday, okay? Now, I made my note here, you know, I'm expanding this to a few more steps to make it, in my view, a little bit clearer, all right? I think it needs to be walked through a little bit more carefully than what they do. So we'll see if you guys agree or disagree. All right. Now, the key thing is, right, is if I look at solving one of these things, right? So if I have this circuit back here, right, what should be the case? If I had a first order circuit, I get a first order differential equation. If I have a second order circuit, what kind of differential equation am I going to get?
Second order.
Power.
Second order. Yeah, second order, right? Not surprising. If I had 3 energy storage elements, I would get a third order circuit, all right? All that kind of stuff. So step 1 is basically to say I should be able to look at a circuit and I should be able to find a differential equation in this form, okay? I should be able to get it in this form, all right? Where X can be essentially one of 2 different things. X of t is the variable I'm concerned about. It can be a capacitor voltage or it can be an inductor current, like that, okay? Now, what this is it says A, B, and C are all constant, Okay. Now, one thing that's really important, A and B need to be positive. All right. If you ever get into a situation where you have negative coefficients in a differential equation, hopefully you know enough from differential equations, but if I have negatives in my differential equations on these coefficients, is that physically possible? What would that, maybe I should ask that question later. If I get negatives, that means that ultimately my transient response would do what? See if anybody knows.
Reach infinity?
It would reach infinity, and that's not possible. All right. If my transient response goes to infinity, that means I would need to store infinite energy on some capacitor or in some inductor. And the universe isn't too kind in that situation, right? The circuit will blow up before that's ever possible. Okay. All right. So your A and B better always be positive. I'm not going to really ask you any questions about that kind of thing, but I say that because if you do your analysis from the circuit and you get that A is equal to -2 and B is equal to 3, you did something wrong. And you did something wrong in your analysis of the circuit. Okay. That's really important. It better be the case that those coefficients are all positive. All right. So that's our first step, is to basically say, I should be able to look at a circuit and I should be able to figure out the differential equation from that circuit. Like I said, Zybook starts out with looking at a series RLC and a parallel RLC and treats those as special, and they are special. But I'm going to treat this from the general perspective like they have in 6.10. I'm going to give you different circuits. They're not necessarily going to be parallel RLC or series RLC. And I'm going to ask you to do the analysis to figure out what the differential equation is. Okay. So I want to start here. I want to say, okay, I've given you this problem. All right. And in particular, I want to do my step one. I want to find the differential equation specifically for t greater than or equal to 0. Okay. And the x of t, the variable I'm interested in here, is the capacitor voltage. So how should I approach that problem? How should I get a differential equation here? Well, before I even start, what do I need to know to do this, right? So there's some key relationships between capacitor current and capacitor voltage, and inductor current and inductor voltage. So how does the capacitor current relate to the capacitor voltage?
C dV to dt.
Yep, C dV C dt, right? So in other words, the current in the capacitor is related to the rate of change of the voltage. That's what that says in words. And what's the similar relationship for an inductor? What's the other relationship? Anybody?
L equals, or sorry, VL equals L DIL over DT.
Yep. All right. V equals L DIL by DT. Okay, those are our two relationships. Now, before I do any analysis ever in a circuit, right, what I do is I mark out the polarities of everything. All right. So V sub C is already marked out for me. All right. Now, in this case, what do I see in this circuit about I sub C and I sub L?
It's equal.
They're the same.
They're the same, right? So I sub L equals I sub C. So that means that V sub L, I could write in this case as L DIC by DT. All right. We're going to need that as we go. Okay. All right. Now, I'm going to call this VR. I'm going to call this VL. All right. Now I'm going to do my KVL for t greater than 0. So if I'm looking at t greater than 0, what should I do with the switch here?
You should close it.
I should close it. All right. All right. Now, if I'm saying I'm writing the differential equation, I don't make any assumptions here about steady state, what the capacitor does in steady state or what the inductor does in steady state. I just write out the differential equation. So how do I do that? How should I start the approach of trying to write that differential equation given that circuit and given the stuff we wrote down? What should be my approach?
You can
Do your KVL loop.
Yeah, let's do KVL, right? 0 equals, so I'll start here and then I'm going to go around in a clockwise direction. So I say negative V sub S, all right, which is negative 24 volts. And then I'm going to say, so because I went minus to plus, and then I go plus to minus on the resistor, and I go plus to minus on the inductor, and I go plus to minus on the capacitor, like that. All right. So I come over here and I say V sub S is equal to V sub R plus V sub L plus V sub C. Now, at this point, I need to start substituting stuff in. All right. So what should I substitute in for V sub R?
ICR.
IR.
Yep, IR. In particular, I'm going to say I sub C times R, right? And there's a reason why I did that, right? So I said IL and IC are the same. So what can I put in for V sub L here?
L DIC over DT.
Yep, L DIC dt plus V sub C. Now, in this case, do I have a differential equation? I guess it sort of is, but is it in that standard form, right? This is the standard form I want. Am I in that standard form yet?
No.
No.
No. What's my next step? How do I get it in that standard form?
You derive it?
You can sub out the IC with the C dVC dt.
Yes, that's right. Yeah, basically what I do is I say, all right, I sub C is C dV dt, so I can substitute that in here, and I can substitute it in here. The key thing is substituting into this middle term is going to turn this equation into second order, right? So in other words, this guy becomes, if I know that, you know, I sub L equals I sub C equals C dVC dt, and I had V sub S equals I.
Dr. Cox,
What's up?
how do we know that the inductor and the capacitor were the same again?
Well, we know that their current is the same.
Oh, is that because it's a series?
Because they're in series, yeah.
Okay, okay.
Right. Once
Fair
that switch closes, those guys are all in series with each other. Right. So I take this result and plug it in here. Right. So I'm going to have V sub S equals RC dVC dt. Right. Plus, what's this middle term going to become? If I plug this in, what do I get?
D square I
LC.
Yep.
D square I
D squared I squared DT.
Well, no. So I'm plugging in for I sub C. So it become, I'm plugging in this guy right here and taking the second derivative of it, right? So this would become D squared VC dt squared plus V sub C. All right. So anytime we're looking at these circuits, we're going to look at lots of examples of them as we go, right? But anytime we're looking at these circuits, right, it basically becomes a situation where, you know, what we need to do when we look at these circuits is essentially to write out a KVL or KCL in some way, and then basically use the relationships, you know, this one here and this one here, all right, to basically figure out how we can manipulate it. And I should be careful, you know, it's not always the case that IL and IC are the same, right? That's not always the case. Right? It all depends on the situation. Those boxed equations are the ones that are always true, okay? All right. Now, is that in our standard form?
Yes.
Almost, not quite. All right. So this gets into, I'm trying to be consistent with Zybooks in the way they do this. Their standard form is to get it like this. This is actually pretty standard, you know, in industry too, is that I try to get there to be a one coefficient on the second derivative term. Okay. So how do I turn this into an equation that'll have a one term on this, or one coefficient on the second derivative? What do I need to do?
Divide everything by LC.
Divide both sides by LC, right? So I'm going to get VS over LC. And this is a constant, right? This would be my C in that equation. Little c, I guess, I don't know, how do I differentiate little c? Okay, equals d squared v sub c dt squared plus, what's going to be R over L dVc dt.
Where are you saying the whole left side is that little c? Vs over LC, that's all little c?
It is, yeah.
Oh, okay.
Yeah, so this is in that general form of A d squared, oh, sorry, not A, d squared Vc dt squared plus A dVc dt plus B Vc equals little c. I don't know how little c, like that, right? So you can do a pattern matching here and say, well, A has to be R over L, and B has to be 1 over LC. I didn't draw that in there. Okay. Zybooks, you know, there's a section on series RLC circuits, it has all kinds of formulas related. There's no one in their right mind knows formulas for these things, right? It is best to be able to look at a circuit and to be able to derive the differential equation from the circuit. All right, there is no reason to jam your head full of all the goofy formulas for series RLC and parallel RLC circuits. All right, when I see you on the street 10 years from now, none of you will remember those formulas, so don't even bother with it. All right, there's some good example problems and things to do in those sections, right? And we'll look at some of those, but I don't find those formulas to be particularly valuable.
I have a question.
Yeah.
So why did you divide by LC again? Sorry, I just forgot.
I just divided it to get it into the standard form, right?
Okay.
Yeah, that's all it is. All right. All right. So if I have that as my differential equation, remember my x, you know, in this case, my x of t, you know, is v sub c, but it could always be IL or it could be VC. Right. Basically, the things that store energy, the inductor current stores energy, the capacitor voltage stores energy. Those are the things that we write differential equations for. All right. Only inductor current, only capacitor voltage. Right? I'm never going to ask you for a differential equation for the inductor voltage or the capacitor current. We only write the differential equations for the energy storage variables. All right. And you will always be explicitly asked, give it for V sub C or I sub L. All right, that's not something you'll have to guess on what variable to write it for, okay? So if I have a differential equation like this, I'm gonna go to your differential equations knowledge, all right? And I have basically a second order differential equation equal to this. That guy's gonna have a solution that I'm gonna say is x of t. And that solution has two components, doesn't it? What are the two components?
Transient and a particular.
Transient and a particular, all right? So it's got a final, so this guy is what I call my particular or steady state solution, right? And it's got another piece, which is the transient solution. So I'm going to call that X transient. Now, what is always in a transient solution of any differential equation? And you're going over this in 2254 with Yahoo, or you will be very soon. But you've taken differential equations to get to this class. What should be true about that transient solution? Always.
It's after the switch closes?
Well, it happens after the switch closes, yeah. What kind of...
eventually becomes zero?
Eventually becomes zero. Yeah, that's right. And unless I had no loss in the system, in which case it doesn't in this case, but normally it's going to go to zero, right? What kind of math function is it?
Logarithmic, I think.
No,
exponential.
Exponential. It's always going to be exponential, okay? And you know, that's closely related to the log, but it's always going to be an exponential. And to find the transient response, what we do is we always say, okay, take the original equation and replace that C with a zero. All right, that's the equation that it solves. And when we have that type of an equation, we always say we guess a solution of the form, we say X transient of T is equal to, the way I write it is I say K e to the ST, where K is not equal to zero. I guess that, okay? So if I plug that K e to the ST into this equation right here, what happens? So if I take if I take this guy and I take the second derivative of this, k e to the st, what's the second derivative of k e to the st? What's the second derivative with respect to time?
S squared.
S squared. Yep, I'm going to get S squared. If I take it, and it's going to be S squared k e to the st.
Can we not use Laplace transforms to solve this?
I could use all sorts of different things, but I don't want to use Laplace transforms, right? There's different ways of thinking about that. I don't want to use that. And I notice, I'm going to put it this way, back with my, yeah, there we go. Back with my original approach here. I changed this to be consistent with Zybooks and I missed that. Okay. I could totally use Laplace transforms, but I don't want to. All right. Effectively, what I'm doing is entirely mathematically the same as that. All right. You'll learn this process. If you didn't see it in differential equations, you'll still see it with Yahoo in 2254. What happens to the middle term? If I take
just S.
Just S, right? So I'll have S times A times K times e to the st, plus for the last term, I just have k e to the st, and that's all equal to 0. Now, what do when I look at this equation, look at everything on the left side there, I've got some common terms there, don't I? What do I have? What's common amongst
the st?
Yeah, there's a k e to the st. So it looks like I have this s squared plus a s plus b times k e to the st, and that's all equal to 0. Now, what do I know about e to the st? What can it never be equal to?
Non-zero.
0.
Never be 0. And I said I didn't want to make a dumb choice. I said k can never be equal to 0. And I've got three things multiplying each other, k, e to the st, and that thing over there, that polynomial. Well, the only thing that could possibly be 0 there is what?
The polynomial.
Yeah, the polynomial, s squared plus as plus b equals 0, right? So what that tells me is I am going to get two roots for s, two values for s, and that's going to give me two exponentials, okay? Now, those roots can be complex. And so people who have taken 2254, if I get complex results for that s, what does that mean? What's it mean if I get complex results for s? Do I still get straight up exponentials like e to the st?
It's a combination of
You get an imaginary and normal number.
Well, I'm gonna get an imaginary part and a real part, which means, I think somebody said it there, I'm gonna get a combination of exponentials and what?
Sinusoids.
Sinusoids. Yeah, that's right. Okay. So ultimately, at the end of the day, right, it comes down to solving this equation. We sometimes call the characteristic equation. All right. And if I just do the quadratic formula, I get the result that is included right there. All right. And the nature of this response relates directly to what is happening underneath that radical, right? If a squared minus 4b is positive, I get one type of result. What happens if a squared minus 4b is negative?
We get an imaginary number.
I get an imaginary number. And if I get imaginary numbers, I get the situation that we talked about earlier, which is I get what I call an underdamped response. Okay, so you know how when we looked at the video earlier, right? We went from a perfect sine wave to a situation where we had a decaying sine wave to a situation where it looked like we just had exponentials. Well, in those cases, what's happening is the values underneath that radical right there are changing. All right. It basically goes from a situation where this root is purely imaginary. So I could think of it this way. I start out with sine waves only, and I get to only x, so only sine and only exponentials. For this, my s values are imaginary only. And here, my s values are real only. Okay. And what we do is sometimes, and just to be consistent with Zybooks, I'm going to put this in kind of a different form. All right. What they do is they basically give us a differential equation in that standard form, like I showed here, right? A times the first order term plus B times the zero order term. And what that ultimately does for me is gives me this result. And they then define this, and this is commonly used. They define this term called alpha, which is A over 2. And they say that B should be equal to a term that is the square root of omega naught. Now, alpha doesn't have any particularly useful name to it, but omega naught does. Omega naught is sometimes called the undamped, or sometimes called the resonant frequency. Okay. So you guys have probably heard the term resonance before. Second order systems can resonate, meaning that they can basically have that kind of sinusoidal variation. All right. So if I use these expressions, right, if I plug in these values, then essentially what I get is that this S guy, these roots can be expressed as negative alpha plus or minus the square root of alpha squared minus omega naught squared. Okay. All right. You can sit down and take these, plug them into here and see where that comes from. But this is the way that we typically write that. Okay. Now, what we do is, I said, looking at figuring out the solution to this guy comes down to what's happening under the radical sign. So figuring out what the response is comes down to that. So the way I look at this is I begin and I look at a couple of different cases. So I've got my general form of the solution there on the top. All right. So if the roots are complex, all right, looking at this expression right here, what would make the roots complex? What has to be true for this to be complex?
A squared minus
Negative.
Yeah, so basically A squared minus omega naught squared would have to be less than 0, or essentially omega naught would need to be greater than alpha. Okay. So when we approach these problems, that's typically what we do, is we're going to look at them and we're going to look at these values for alpha and omega naught. We're going to figure out which one is which. Now, the form of the solution, you'll talk about how to manipulate this stuff. If you didn't see it in differential equations, you'll sure as hell see it in 2254 with Yahoo, where essentially what you'll be doing is figuring out, okay, how do I get from this K e to the ST, I will get to somehow that thing, okay? What I've shown right here. So basically so the transient response is just this piece right here. This is my steady state, okay? We're gonna talk about steady state more on Wednesday, okay? This is my steady state solution. In words, tell me something about e to the negative alpha t times this. If I looked at what that looked like as a function of time, what would that transient response look like? What would this guy look like?
It will be approaching 0.
Be approaching, it'd be what? I cut somebody off. Sine or cosine, but what would its amplitude look like over time?
It would be decreasing.
Yeah, it would be this guy. This is our underdamped situation, right? Where I've got some loss in the system and this guy is sort of slowly decreasing. All right, so this guy uses another term in here, omega D. That's the frequency here. Omega D is the square root of omega naught squared minus alpha squared, okay? So we're going to use that later on. But basically, the two key things here is this happens when the omega naught value is greater than the alpha value. Again, these are like, I was going to say these are Greek terms. They are Greek terms. Yeah, right. So, this is going to seem like Greek to you, and it is, right? But there's not a lot. I try to distill it down to a smallest number of formulas that I can kind of think of to be able to keep track of this. Now, what's true about this D1 and D2 here? What are those? What are those guys?
The amplitudes?
The amplitudes. And how do those amplitudes at this point are unknown, right? There's two unknown amplitudes. How do I get those unknown amplitudes?
Initial condition.
Initial conditions. This is a second order differential equation. So how many initial conditions am I going to need?
2.
2, right? I'm going to need 1 for X. And what's the other one that I'm going to need?
T.
Not for T. I need 1 for X of T. So at X of 0. And I also need an initial condition for what?
X prime T.
Yeah, the derivative, right? I need 1 for the derivative as well. Okay. All right. So more to say about that piece on Wednesday. All right. Now, the next situation I get into is if the roots are real and equal. We call that critically damped. Okay. In that case, the solution has the form here. I still have 2 unknown coefficients. This guy here is my transient response. Now, if I have 2 roots that are real and equal, what has to be true about alpha and omega there?
They're equal.
They're equal. Alpha equal to omega naught. Now, I don't talk about this case a whole lot because it's stupid. All right. The reason I say it's stupid, if you think hard about this, and it may not be immediately obvious to you just given the experiences that you guys have had, but this requires very extremely precise values of inductors and capacitors and resistors at a level of precision that never happens in the real world. All right. So what happens a lot more is that I get underdamped, or I get my case 3, which is overdamped, which is the case where I have roots that are real and distinct. In other words, what does the word distinct mean? When I say they're real and unique, right? They're 2 different numbers. All right. So in this case, what's true about the relationship between alpha and omega naught?
Alpha is greater.
Alpha is greater. Okay. And if I know alpha is greater, now I get a situation where I have a purely exponential response. This was like the case where I had a whole lot of loss in that pendulum system, or a whole lot of loss in that RLC circuit. And my response looked a lot more first order because it's basically just exponentials. All right. So it's sometimes hard to tell the difference between an overdamped second order system and just a regular first order system. Okay. Now, that's really all that it comes down to, right? Now, our total solution is a combination of the transient response with X of infinity, which is what we call our final value, which we get from steady state analysis. We're going to do some of that on Wednesday, where we look at the circuit and we say, well, in steady state, the capacitor is an open, the inductor is a short. You know, what are the currents and voltages going to be in that situation? And we're basically going to say, we're going to look at the circuit, we're going to say, what's alpha and omega naught? And then we're going to look at this guy and say, well, which form of the solution do we use? And then we got to figure out what those unknowns are, okay? All right, so, you know, there's series RLC circuit, there's all kinds of different circuits, right? Essentially what we see is kind of what we already talked about here, right? So in this case, the series RLC circuit, if it's underdamped, right, alpha less than omega naught, I get this kind of overshooting, right, where this guy comes up and he overshoots and then comes back down. Then as I go to an overdamped scenario, what I see is he's usually slower to rise, but he's not as wild. All right, that's kind of a very non-technical term, but a lot of times I consider this underdamped response to be quote unquote wild, right? And there's reasons why I call it that. Because usually that underdamped response is fast, but you know, that voltage rising that high sometimes can be really bad. All right, very oftentimes when I get these kinds of underdamped responses, they're usually not desired. Now, we're not design engineers here, we're just learning engineers, so we don't need to worry about that just yet. All right, but it is important to remember what the differences just qualitatively are between the different shapes of these things. All right.
Are these cases only unique to voltage? Like, is
Nope.
it only,
They
can
apply.
we say,
So that's why I write this as X, right? Because so any second order system, this is what the responses look like. So voltage on a capacitor, inductor current, those both could have the same look. Okay. So even in this circuit I have right here, I would have the same type of look for the inductor current. All right. You know, the same general shape would apply. If I had a mechanical system, right, like back when I showed that video early on, I had that kind of behavior for a position, you know, for an angle, right? So in any second order system, the variables always have these sorts of values. For us, it's always going to come down to an IL or a VC.
Okay.
Okay. All right. So essentially the way I look at this is, and I start from this case 0 to case 3, right? Basically, as I go from undamped to overdamped, what increases is my loss. And I go from essentially a pure sine wave to a decaying sine wave to essentially what amounts to just an exponential. All right. That's the way that I think about these things. Okay. There's a series RLC, there's a parallel RLC, and then there's all kinds of stuff in between. Okay. So we're gonna dive into all of those. Now, on Wednesday, I'm going to walk through a more complete process. Today, we really only talked about the first 2 steps. How do I get the basic form of the differential equation, and how do I get its basic solution? Then we're going to talk through, you know, the rest of these steps, and then we're going to be going through a lot more examples to get ourselves, you know, used to how to deal with these things. So let's take a little bit of an example here. All right, so let's try to take a stab at this guy in the time we've got left here. So I want to find the differential equation in this case for IL of t for t greater than or equal to 0. And then I want to try to solve that guy. All right, so let's take a stab at this. So if I want to find IL of t for t greater than or equal to 0, what does the circuit look like in that condition? Where's the switch for t greater than or equal to 0?
Go to the number 2.
Goes to number 2, right? So that means that this guy would look like this. So here's 60 ohms. Here is 12 volts. Here's 30 ohms. Here's L. Here's C. Okay. Now, there's no reason why I couldn't analyze this circuit as it is. And let me just write up here, V sub C. And my goal is to get an equation for I sub L right there. All right. So there's no reason why I couldn't go with this circuit, but I don't like it. It's going to be more complicated. What I want to do is I want to turn everything to the left of this dashed line. I want to get a Norton equivalent for everything to the left side of that guy. All right, you guys may want to mute if you're talking. Sounds like somebody's in the back. All right. Don't want any toilets flushing or something. All right. So if I look,
why are you picking the left side?
Well, because I want to turn everything on the left side into a current source and a single resistor. And so I want to turn this circuit into basically a current source, resistor, inductor, and capacitor. Don't necessarily have to, but I want to.
Okay.
It's going to ultimately makes my life a little bit easier, right, when I do my analysis. So if I want to turn that left side into a Norton equivalent, that's what it's going to look like. It's going to look like what I have up here. So if I do that, what do I get here? How would I find the Norton equivalent? So let me jump over.
You want source transformation?
Well, all right. So Norton equivalent, I'm looking at this guy and I say, well, what's the resistance I see looking into those terminals? What would that be? What's the resistance seen looking into the terminals?
20 ohms. Parallel. 30.
They're in parallel, right? Because it's basically the current that's seen by a current source over here that passes in and then splits between the 60 and the 30. So I got 60 in parallel with 30, which if you do that math later, you'll see that that's 20, okay? What about, so this is my R equivalent. Now what happens if I put a short circuit right here? That's how I get my short circuit current, right? Put a short circuit right there. What's that going to be? This was a 12 volt.
No current method.
So ISC is this. Be what?
0.6 amps.
Not quite.
No current.
60 over 20.
And the 12 over 30 over 60.
So what? So in this case, does the 30 ohm matter?
No.
It doesn't matter.
Nope. So I would just have this, right? That would be my circuit effectively. So this guy would become 12 over 60 or 0.2 amps. Okay. So in other words, I've converted this circuit now into 0.2 and then this. Okay.
Couldn't you also convert the 12 volt source and 60 ohm resistor into a Norton equivalent and then just do the parallel resistor that way?
Yeah, I mean, it's this, you know, I'm doing it in one step rather than two, I guess. I mean, yeah, it's basically the same approach.
Okay.
Okay. All right, well, so with that there, now I want to write a differential equation for that circuit. How would I start, do you think, to write a differential equation for that circuit?
KCL.
KCL, right? This guy would do KCL. And I'm going to say in this case, right? So I start out by writing everything like I have here. What I know in this case is my 0.2 equals I sub R plus I sub L plus I sub C. Okay, make sense? Sure. All right, what do I know about the relationship here between I sub L, I sub C, all that kind of stuff? I need to write out my other basic relationships, right? I sub C equals what? What's that always equal to?
C
dV dt.
Yeah, C dV dt. And I know that V sub L is L dIL by dt, right? And in this case, what do I know about VL and VC? The voltage across the capacitor and the voltage across the inductor. What has to be true about those?
They're the same.
They're the same.
They have to be equal.
Yeah, they have to be equal to each other. So that means in this particular case, I can say that I have 0.2 equals V sub C over R, that's the capacitor, or the resistor current, plus I sub L plus, we said I sub C, that's C dVc dt. But since we know that V sub C equals V sub L, how can I use that to turn this into a second order equation? How does that become second order?
Substitute VC.
Yeah, substitute for VC, right? So this guy is going to become L over R dIL by dt plus IL plus LC dVc dt squared. Or sorry, dIL by dt squared. Okay, now that's a second order equation, right? So now to get it in my standard form, what do I have to do to get that guy to standard form?
Divide by LC.
Divide by LC. So I'm going to get 0.2 divided by LC equals d squared IL by dt squared plus 1 over RC DIL by dt plus IL. Now that's a second order differential equation divided by LC. Now what we have to do is get to our second step, which is to say, okay, now I need to solve that differential equation, which means that I need to look at this guy and say, okay, well, let's determine the alpha and omega values from that and determine if it's underdamped, overdamped, so on and so forth. All right. So
I have a question.
So
Dr. Cox.
We'll jump into taking a look at that that next step a little bit on Wednesday. All right, that last step of doing that analysis. But I'll stop here for today. and then I'll take some questions on this if you guys have it. So there's a question I cut off there, but if you want to go ahead and ask that now.
Yeah, I was just wondering, like, so, like, intuitively, why did you decide to do the Norton equivalent? Because I mean, I'm looking at it right now. I could be wrong, but wouldn't the differential equation be like exactly the same? Like you'll get 0.2 amps equals V, or whatever the currents were, IR, IL, IC.
Yeah, so I should get the same, so it's the same circuit. Norton equivalent means it's equivalent to what I already have. So I would get the same result. But what I would find is that if I didn't make a Norton equivalent, there would be more step. I need to do more than just one KCL to get the result here. I would need to do, you know.
It'd make it more complex to get the differential equation, wouldn't it?
It would make it, yeah, it would be some more steps to get the differential equation, but fundamentally nothing wrong with it. Right. It's just a little bit of it. And that's where you use that junk. So you learned all this crap in that you thought was crap or useless in network one, like Norton equivalent, Thevenin equivalent resistances, all that stuff. But where that really becomes useful is when you can kind of simplify some of those steps like we're doing here by making that Norton. It's a good question though. It would still give me the same result.
So that's because the Norton equivalent is in the parallel with the capacitor and inductor. It's an easier for phi because they have the same V, right?
Yeah, and don't get bogged down in the Norton piece, right? That's not the important thing. I wanted to show that because it's an important thing to know, right? But I certainly could have done it without doing that. Okay. And like I said, at the very beginning on Wednesday, we'll go through and we'll get the solution to that guy. All right. Any other questions you guys have? Okay. All right. Well, if you guys have no other questions, I am going to stop and I can stick around for probably another 10-ish minutes if you guys